Quantum electrodynamics (QED) is a fundamental theory in physics that describes how light and matter interact. It is a quantum field theory of the electromagnetic force, which is one of the four fundamental forces of nature. Let's break down its key aspects and how it came to be. 1. Basic concept of QED. QED is the quantum theory of the electromagnetic field. It explains how electrically charged particles, such as electrons and positrons, interact with each other and with photons, which are the particles of light. This theory combines the principles of quantum mechanics with the theory of special relativity to provide a comprehensive framework for understanding electromagnetic interactions. 1. 2. Historical development. Early 20th century. The foundations of QED were laid in the early 20th century. In 1928, British physicist Paul Dirac formulated a wave equation that described the behavior of electrons, incorporating both quantum mechanics and special relativity. 2. 1930s. During the 1930s, further developments were made by physicists such as Wolfgang Pauli, Eugene Wigner, and Enrico Fermi. They contributed to the understanding of how particles interact through the exchange of photons. 1. 1940s. The theory faced significant challenges due to infinities that appeared in calculations. These issues were resolved in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who independently developed a method called renormalization. This technique allowed for the removal of infinities and made the theory consistent and predictive. 2. 3. Key principles of QED. Photon exchange. In QED, interactions between charged particles occur through the exchange of virtual photons. These photons are not directly observable but mediate the electromagnetic force between particles. 2. Feynman diagrams. Richard Feynman introduced a graphical representation of particle interactions known as Feynman diagrams. These diagrams simplify the complex calculations involved in QED by visually representing the paths of particles and their interactions. 1. Renormalization. This process involves adjusting the parameters of the theory to account for the effects of interactions at different energy scales. Renormalization ensures that the predictions of QED match experimental observations with high precision. 2. 4. Experimental verification. QED is one of the most accurately tested theories in physics. Its predictions have been confirmed to an extraordinary degree of precision. For example, the anomalous magnetic moment of the electron and the Lamb shift in the energy levels of hydrogen are both phenomena that QED accurately describes and predicts. 1. 5. Significance and applications. QED has profound implications for our understanding of the universe. It provides the theoretical foundation for much of modern physics, including the Standard Model, which describes the fundamental particles and forces. QED also has practical applications in fields such as electronics, optics, and quantum computing. 2. In summary, quantum electrodynamics is a cornerstone of modern physics, providing a detailed and accurate description of how light and matter interact. Its development involved overcoming significant theoretical challenges and has led to some of the most precise predictions in science. Quantum electrodynamics (QED) is specifically the quantum field theory of the electromagnetic force. To understand how it relates to other fundamental forces, let's look at the broader framework of particle physics. 1. The four fundamental forces. There are four fundamental forces in nature. Electromagnetic force, described by QED, it governs the interactions between charged particles and photons. Weak nuclear force, responsible for processes like beta decay in radioactive atoms. It is described by the Electroweak theory, which unifies the weak force with the electromagnetic force. Strong nuclear force holds protons and neutrons together in atomic nuclei. It is described by quantum chromodynamics (QCD). Gravitational force, the force of attraction between masses. It is described by general relativity, not yet fully reconciled with quantum mechanics. 2. Electroweak unification. QED is part of the Electroweak theory, which unifies the electromagnetic force and the weak nuclear force. This unification was developed in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, who showed that at high energies, these two forces merge into a single force. This theory was experimentally confirmed by the discovery of the W and Z bosons in the 1980s. 3. Quantum chromodynamics (QCD). While QED deals with the electromagnetic force, QCD is the quantum field theory that describes the strong nuclear force. QCD explains how quarks and gluons interact to form protons, neutrons, and other hadrons. Unlike QED, where photons are the force carriers, QCD's force carriers are gluons. For the Standard Model, QED, QCD, and the Electroweak theory are all components of the Standard Model of particle physics. The Standard Model is a comprehensive theory that describes 3 of the 4 fundamental forces, excluding gravity, and classifies all known elementary particles. It successfully explains a wide range of phenomena and has been confirmed by numerous experiments. 5 are challenges with gravity. One of the major challenges in modern physics is reconciling quantum mechanics, including QED, with general relativity, which describes gravity. Efforts to develop a quantum theory of gravity, such as string theory and loop quantum gravity, are ongoing but have not yet been fully successful. Summary: QED is a crucial part of the broader framework of particle physics, fitting into the Standard Model alongside QCD and the Electroweak theory. While it provides a detailed understanding of the electromagnetic force, integrating it with the other forces, especially gravity, remains a significant challenge in theoretical physics. Early foundations. Classical electrodynamics. Before QED, the behavior of electromagnetic fields and their interactions with matter were described by classical electrodynamics, primarily through Maxwell's equations. These equations, formulated in the 19th century, describe how electric and magnetic fields propagate and interact with charges. Quantum mechanics. The early 20th century saw the development of quantum mechanics, which provided a new framework for understanding the behavior of particles at atomic and subatomic scales. Key figures like Max Planck, Niels Bohr, and Werner Heisenberg contributed to this field. 2. Dirac's contribution. Dirac equation. In 1928, Paul Dirac formulated the Dirac equation, which describes the behavior of electrons and incorporates both quantum mechanics and special relativity. This equation predicted the existence of antimatter and provided a basis for understanding the spin of electrons. 1. Quantization of the electromagnetic field. Dirac also worked on quantizing the electromagnetic field, treating it as an ensemble of harmonic oscillators. This approach introduced the concept of creation and annihilation operators, which are fundamental to quantum field theory. 1. 3. Challenges and infinities. Initial problems. Early attempts to develop a quantum theory of electromagnetism faced significant challenges. Calculations often resulted in infinities, making the theory appear inconsistent. These problems were highlighted by physicists like Robert Oppenheimer and Victor Weisskopf. 1. Perturbation theory. Physicists used perturbation theory to approximate solutions to complex quantum mechanical problems. However, higher-order calculations in QED led to divergent series, further complicating the theory. 1. 4. Renormalization. Breakthroughs in the 1940s. The key breakthrough in resolving these issues came in the late 1940s. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga independently developed the technique of renormalization. This method allowed physicists to systematically remove infinities from calculations, making QED a consistent and predictive theory. 2. Feynman diagrams. Richard Feynman introduced Feynman diagrams, a graphical representation of particle interactions. These diagrams simplified complex calculations and provided intuitive insights into the processes described by QED. 2. 5. Experimental verification. Precision tests. QED has been subjected to rigorous experimental tests. One of the most notable is the measurement of the anomalous magnetic moment of the electron, which agrees with QED predictions to an extraordinary degree of precision. Another key test is the Lamb shift, a small difference in energy levels of hydrogen atoms that QED accurately predicts. 2. Technological advances. Advances in experimental techniques, such as microwave spectroscopy, allowed for precise measurements that confirmed the predictions of QED. 1. 6. Significance and impact. Foundation of modern physics. QED is a cornerstone of the Standard Model of particle physics, which describes the fundamental particles and forces, excluding gravity. It has provided deep insights into the nature of electromagnetic interactions and has influenced the development of other quantum field theories. 2. Practical applications. Beyond its theoretical significance, QED has practical applications in various fields, including electronics, optics, and quantum computing. It has also paved the way for technologies such as lasers and semiconductor devices. 2. In summary, the creation of quantum electrodynamics was a complex process that involved overcoming significant theoretical challenges and achieving remarkable experimental precision. It stands as one of the most successful and accurate theories in physics, providing a detailed understanding of how light and matter interact. Quantum chromodynamics (QCD) is the theory that describes the strong interaction, one of the 4 fundamental forces in nature. It explains how quarks and gluons interact to form protons, neutrons, and other hadrons. Let's delve into the details of QCD and its development. 1. Fundamental concepts. Quarks. Quarks are elementary particles that come in 6 flavors: up, down, charm, strange, top, and bottom. They are the building blocks of hadrons, for example, protons and neutrons. Gluons. Gluons are the force carriers of the strong interaction. They mediate the force between quarks, similar to how photons mediate the electromagnetic force in quantum electrodynamics (QED). Color charge. Unlike electric charge in QED, QCD involves a property called color charge. Quarks come in 3 colors: red, green, and blue, while gluons carry a combination of color and anticolor. 2. Historical development. Early theories. In the 1960s, Murray Gell-Mann and George Zweig independently proposed the quark model to explain the particle zoo of hadrons observed in experiments 1. They introduced the concept of quarks as the fundamental constituents of hadrons. Gauge theory. QCD is a type of quantum field theory known as a non-abelian gauge theory, with the symmetry group SU3. This was developed in analogy to QED but with more complex interactions due to the non-abelian nature of the SU3 group 1. Asymptotic freedom. In 1973, David Gross, Frank Wilczek, and David Politzer discovered that the strength of the strong interaction decreases at higher energies, a property known as asymptotic freedom. This discovery was crucial for the acceptance of QCD and earned them the Nobel Prize in Physics in 2042. 3. Key properties of QCD. Color confinement. Quarks and gluons are never found in isolation, they are always confined within hadrons. This phenomenon is known as color confinement. The force between quarks does not diminish with distance, leading to the creation of quark-antiquark pairs when attempting to separate them. 1. Chiral symmetry breaking. QCD predicts that the vacuum state of the theory breaks chiral symmetry spontaneously. This results in the generation of masses for hadrons that are much larger than the masses of the constituent quarks. 1. 4. Mathematical framework. Lagrangian of QCD. The QCD Lagrangian describes the dynamics of quarks and gluons. It includes terms for the quark fields, gluon fields, and their interactions. The Lagrangian is invariant under local SU3 gauge transformations, reflecting the symmetry of the theory. 1. Feynman diagrams. Similar to QED, QCD interactions can be represented using Feynman diagrams. However, the diagrams in QCD are more complex due to the self-interactions of gluons, which do not occur in QED. 1. 5. Experimental evidence. Deep inelastic scattering. Experiments in the 1960s and 1970s, such as deep inelastic scattering at SLAC, provided evidence for the existence of quarks and the validity of QCD. These experiments showed that protons and neutrons have an internal structure consistent with quarks too. Lattice QCD. Lattice QCD is a computational approach that discretizes spacetime on a lattice to solve the equations of QCD numerically. It has been successful in predicting hadron masses and other properties with high precision too. 6. Applications and implications. Nuclear physics. QCD is fundamental to understanding the structure and interactions of atomic nuclei. It explains the binding of protons and neutrons within nuclei through the residual strong force, also known as the nuclear force. 1. High-energy physics. QCD plays a crucial role in high-energy physics experiments, such as those conducted at the Large Hadron Collider, LHC. It helps in understanding particle collisions and the formation of jets too. In summary, quantum chromodynamics is a comprehensive theory that describes the strong interaction between quarks and gluons. It has a rich mathematical structure and has been confirmed by numerous experiments, making it a cornerstone of the standard model of particle physics. The QCD confinement hypothesis is a fundamental concept in quantum chromodynamics (QCD), which describes the strong interaction between quarks and gluons. Let's break down this hypothesis in detail. 1. Basic idea of confinement. Confinement refers to the phenomenon where quarks and gluons are never found in isolation. Instead, they are always confined within larger particles called hadrons, such as protons and neutrons. This means that quarks and gluons cannot be directly observed under normal conditions. 1. 2. Color charge and gluon fields. Color charge. In QCD, quarks possess a property called color charge, which comes in 3 types: red, green, and blue. Gluons, the force carriers of the strong interaction, also carry color charge. Gluon fields. Unlike the electromagnetic force, where the force-carrying photons are neutral, gluons themselves carry color charge. This leads to a unique behavior of the gluon field. 1. 3. Mechanism of confinement. Flux tubes. When quarks are pulled apart, the gluon field between them forms a narrow tube-like structure called a flux tube. the energy required to stretch this tube increases with distance, unlike the electromagnetic force, which decreases with distance. String breaking: as the distance between quarks increases, it becomes energetically favorable to create a new quark-antiquark pair rather than extending the flux tube indefinitely. This process prevents quarks from being isolated. 1. For experimental evidence. Hadronization: when quarks are produced in high-energy Collis ions, they quickly combine with other quarks to form hadrons. This process, known as hadronization, is a direct consequence of confinement. Jets in particle detectors: instead of seeing individual quarks, scientists observe jets of hadrons. These jets are clusters of particles that result from the hadronization process. 1. 5. Theoretical framework. Wilson loop: the confinement hypothesis can be studied using the Wilson loop, a mathematical tool that describes the path of a quark-antiquark pair in spacetime. In a confining theory, the action of the Wilson loop is proportional to its area, indicating that the force between quarks remains constant regardless of their separation. 1. Lattice QCD: numerical simulations using lattice QCD, where spacetime is discretized into a grid, have provided strong evidence for confinement. These simulations show that the potential between quarks grows linearly with distance, supporting the flux tube model. 2. 6. Unresolved questions. Analytic proof: despite strong experimental and numerical evidence, there is no complete analytic proof of confinement in QCD. The phenomenon is understood qualitatively, but a rigorous mathematical derivation remains an open problem in theoretical physics. 2. Summary: the QCD confinement hypothesis explains why quarks and gluons are never found in isolation but are always confined within hadrons. This phenomenon is a result of the unique properties of the gluon field and the color charge in QCD. While there is substantial evidence supporting confinement, a complete theoretical proof is still lacking. Confinement in quantum chromodynamics (QCD) has profound effects on the properties of hadrons, which are particles composed of quarks held together by the strong force. Let's explore how confinement influences various aspects of hadrons. 1. Mass of hadrons. Quark masses versus hadron masses: the masses of individual quarks are much smaller than the masses of the hadrons they form. For example, the up and down quarks that make up protons and neutrons have masses of a few MeV/C2, while protons and neutrons have masses around 938 MeV/C2. The majority of a hadron's mass comes from the energy of the gluon field and the strong interaction, not just the quark masses. Dynamic mass generation: confinement leads to the generation of mass through the dynamics of the strong interaction. This is a result of the energy stored in the gluon fields and the interactions between quarks. 2. Charge and color neutrality. Color neutrality: hadrons must be color neutral, meaning they do not carry a net color charge. This is a direct consequence of confinement. In baryons, such as protons and neutrons, 3 quarks combine in such a way that their color charges cancel out. In mesons, a quark and an antiquark pair up to achieve color neutrality. Electric charge: the electric charge of hadrons is determined by the sum of the charges of their constituent quarks. For example, a proton is composed of 2 up quarks, each with a charge of +2/3, and 1 down quark with a charge of -1/3, resulting in a total charge of +1. 3. Size and structure. Finite size: hadrons have a finite size, typically on the order of a femtometer, 10^15 meters. This size is determined by the spatial distribution of the quarks and the gluon field within the hadron. Internal structure: the internal structure of hadrons is complex, with quarks constantly interacting through the exchange of gluons. This dynamic interaction gives rise to a rich internal structure that can be probed through high-energy scattering experiments. 4. Binding energy. Residual strong force: the strong force that confines quarks within hadrons also manifests as a residual force between hadrons, known as the nuclear force. This residual force is responsible for binding protons and neutrons together in atomic nuclei. Binding energy contribution: the binding energy of hadrons contributes significantly to their overall mass. This energy arises from the interactions between quarks and gluons and is a key factor in the stability of hadrons. 5. Excited states and resonances. Excited states: hadrons can exist in excited states, where the quarks have higher energy levels. These excited states are often short-lived and decay into lower-energy hadrons. The spectrum of these states provides important information about the strong interaction and confinement. Resonances: some excited states of hadrons appear as resonances in scattering experiments. These resonances are temporary states that decay rapidly, providing insights into the dynamics of quark interactions and the nature of confinement. Summary: confinement in QCD fundamentally shapes the properties of hadrons, influencing their mass, charge, size, structure, binding energy, and excited states. It ensures that quarks and gluons are never found in isolation, leading to the rich and complex behavior observed in hadronic matter. Confinement in quantum chromodynamics (QCD) significantly influences the behavior and properties of the strong nuclear force. Here's a detailed explanation of how confinement affects this fundamental force. 1. Nature of the strong nuclear force. Fundamental strong force. The strong nuclear force, also known as the strong interaction, is the force that binds quarks together to form protons, neutrons, and other hadrons. This force is mediated by gluons, which carry the color charge. Residual strong force. The residual strong force, or nuclear force, is the force that holds protons and neutrons together within atomic nuclei. It is a residual effect of the fundamental strong force acting between quarks. 1. 2. Confinement and color charge. Color confinement. Confinement ensures that quarks and gluons are never found in isolation. They are always confined within hadrons, making these particles color neutral. This is because the strong force increases with distance, unlike other forces that diminish with distance. 1. Flux tubes. When quarks are pulled apart, the gluon field between them forms a flux tube. The energy required to stretch this tube increases linearly with distance, leading to the creation of new quark-antiquark pairs if the separation becomes too large. 1. 3. Impact on hadron properties. Mass and binding energy. The mass of hadrons is largely due to the energy of the gluon field and the interactions between quarks, rather than the masses of the quarks themselves. Confinement contributes to the binding energy that holds quarks together within hadrons. 1. Hadronization. In high-energy colisions, quarks and gluons produced are quickly confined into hadrons. This process, known as hadronization, results in the formation of jets of particles rather than isolated quarks. 1. 4. Residual strong force in nuclei. Nuclear binding. The residual strong force is responsible for binding protons and neutrons together in atomic nuclei. This force acts over a short range, about 1 to 3 meters, and is much stronger than the electromagnetic repulsion between protons. 1. Meson exchange. The residual strong force is mediated by the exchange of mesons, such as pions, between nucleons. This exchange is a consequence of the underlying quark-gluon interactions and confinement. 1. 5. Experimental observations. Deep inelastic scattering. Experiments such as deep inelastic scattering have provided evidence for the internal structure of protons and neutrons, consistent with quark confinement. These experiments show that quarks are tightly bound within hadrons. 1. Lattice QCD. Numerical simulations using lattice QCD have confirmed the confinement hypothesis by showing that the potential between quarks grows linearly with distance, supporting the flux tube model. 1. Summary: confinement in QCD ensures that quarks and gluons are always confined within hadrons, profoundly affecting the properties of the strong nuclear force. It leads to the formation of color-neutral hadrons, contributes to the mass and binding energy of these particles, and results in the residual strong force that binds atomic nuclei together. The residual strong force, also known as the nuclear force, plays a crucial role in the structure and stability of neutron stars. Here's a detailed explanation of how this force affects neutron stars. 1. Formation of neutron stars. Supernova collapse. Neutron stars are formed from the remnants of massive stars that have undergone a supernova explosion. During the collapse, protons and electrons combine to form neutrons, resulting in a star composed almost entirely of neutrons. 1. Neutron degeneracy pressure. The collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle, which prevents neutrons from occupying the same quantum state. 1. 2. Role of the residual strong force. Binding neutrons. The residual strong force is responsible for binding neutrons together within the neutron star. This force acts over very short distances, about 1 to 3 meters, and is much stronger than the electromagnetic repulsion between protons. 2. Nuclear matter. In the extremely dense environment of a neutron star, the residual strong force ensures that neutrons remain bound together, preventing the star from collapsing further under its own gravity. 2. 3. Equation of state. Pressure and density relationship. The equation of state, EOS, of neutron star matter describes the relationship between pressure and density. The residual strong force significantly influences the EOS, determining the star's structure and stability. 2. Stiffness of the EOS. A stiffer EOS, where the pressure increases rapidly with density, results in a larger and more massive neutron star. The residual strong force contributes to this stiffness by providing additional pressure to counteract gravitational collapse. 2. For neutron star crust. Crust composition. The outer crust of a neutron star consists of a lattice of nuclei immersed in a sea of electrons. The residual strong force binds these nuclei together, while the inner crust contains a mixture of neutrons, protons, and electrons too. Nuclear pasta. At the base of the crust, the matter can form exotic structures known as nuclear pasta, for example, rods, slabs, due to the competition between the residual strong force and the Coulomb force too. 5. Core of neutron stars. Superfluid neutrons. In the core, neutrons may form a superfluid state, where they flow without viscosity. The residual strong force plays a role in the interactions that lead to this superfluidity too. Exotic matter. At even higher densities, the core might contain exotic forms of matter, such as hyperons, particles containing strange quarks, or deconfined quark matter. The interactions involving the residual strong force are crucial in determining the properties of this exotic matter too. 6. Astrophysical observations. Mass and radius measurements. Observations of neutron star masses and radii provide insights into the EOS and the role of the residual strong force. For example, the discovery of neutron stars with masses around 2 solar masses suggests a relatively stiff EOS too. Gravitational waves. Mergers of neutron stars, detected through gravitational waves, offer additional information about the internal structure and the forces at play, including the residual strong force too. Summary. The residual strong force is essential for the stability and structure of neutron stars. It binds neutrons together, influences the equation of state, and affects the properties of both the crust and core of neutron stars. Understanding this force helps scientists interpret astrophysical observations and gain insights into the behavior of matter under extreme conditions. The electroweak theory is a fundamental framework in particle physics that unifies 2 of the 4 known fundamental forces, the electromagnetic force and the weak nuclear force. This theory is a cornerstone of the standard model of particle physics. Let's explore its development and key concepts in detail. 1. Fundamental forces. Electromagnetic force. This force acts between charged particles and is mediated by photons. It is responsible for phenomena such as electricity, magnetism, and light. Weak nuclear force. This force is responsible for processes like beta decay in radioactive atoms. It acts over very short distances, typically less than the size of an atomic nucleus, and is mediated by W and Z bosons. 2. Historical development. Early theories. In the mid-20th century, physicists sought to develop a unified theory that could describe both the electromagnetic and weak forces. The challenge was to create a theory that was both gauge invariant and René-Amélizable. Key contributors, Sheldon Glashow, Abdus Salam, and Steven Weinberg made significant contributions to this effort. They independently developed a theory that unified the electromagnetic and weak forces, for which they were awarded the Nobel Prize in Physics in 1991. 3. Gauge symmetry and the electroweak force. Gauge symmetry. The electroweak theory is based on the principle of gauge symmetry, specifically the SU2XU1 symmetry group. This symmetry describes how the electroweak force behaves under certain transformations. Unified force. At high energies, the electromagnetic and weak forces merge into a single electroweak force. This unification occurs at energy levels around 246 GeV, which corresponds to temperatures of approximately 10^15 K1. 4. Spontaneous symmetry breaking. Higgs mechanism. The electroweak theory incorporates the Higgs mechanism to explain how particles acquire mass. This mechanism involves the Higgs field, which permeates all of space. When particles interact with this field, they gain mass. Massive gauge bosons. The Higgs mechanism breaks the electroweak symmetry, resulting in the W and Z bosons acquiring mass, while the photon remains massless. This explains why the weak force is short-ranged and the electromagnetic force is long-ranged too. 5. Experimental confirmation. Neutral currents. The existence of neutral currents, predicted by the electroweak theory, was confirmed in 1973 through neutrino scattering experiments conducted by the Gargamel collaboration. 1. Discovery of W and Z bosons. In 1983, the W and Z bosons were discovered at CERN by the UA1 and UA2 collaborations. These discoveries provided strong experimental support for the electroweak theory too. 6. Significance and impact. Standard model. The electroweak theory is a crucial component of the standard model of particle physics, which describes the fundamental particles and their interactions, excluding gravity. Technological advances. The theory has led to significant technological advancements, including the development of particle accelerators and detectors used in high-energy physics experiments too. Summary. The electroweak theory unifies the electromagnetic and weak nuclear forces into a single framework, explaining how particles acquire mass through the Higgs mechanism and predicting the existence of W and Z bosons. This theory has been experimentally confirmed and is a fundamental part of the Standard Model, shaping our understanding of the universe at the most fundamental level. The electroweak theory plays a crucial role in explaining how particles acquire mass through the Higgs mechanism. Here's a detailed explanation of this relationship. 1. Electroweak unification. Unified force. The electroweak theory unifies the electromagnetic force and the weak nuclear force into a single framework. This unification is described by the SU2XU1 gauge symmetry, which combines the weak isospin SU2 and hypercharge U1 symmetries. Gauge bosons. The theory predicts 4 gauge bosons: the photon, gamma, the W+, W, and Z bosons. These bosons mediate the electromagnetic and weak interactions. 2. Higgs mechanism. Higgs field. The Higgs mechanism introduces a scalar field known as the Higgs field, which permeates all of space. Particles interact with this field, and the strength of their interaction determines their mass. Spontaneous symmetry breaking. At high energies, the electroweak symmetry is unbroken, and all particles are massless. As the universe cools, the Higgs field acquires a non-zero vacuum expectation value, breaking the electroweak symmetry spontaneously. 3. Massive gauge bosons. W and Z bosons. The breaking of electroweak symmetry results in the W and Z bosons acquiring mass. The photon remains massless because it is associated with the unbroken U1 electromagnetic symmetry. Mass terms. The masses of the W and Z bosons are given by the interaction of the gauge fields with the Higgs field. The W bosons have a mass of approximately 80.4 GeV/C2, and the Z boson has a mass of about 91.2 GeV/C2. 4. Fermion masses. Yukawa couplings. The masses of fermions, such as quarks and leptons, are generated through their interactions with the Higgs field. These interactions are described by Yukawa couplings, which determine the strength of the interaction and, consequently, the mass of the fermion. Diverse masses. Different fermions have different Yukawa couplings, leading to a wide range of masses. For example, the top quark has a much larger Yukawa coupling than the electron, resulting in a significantly higher mass. 5. Experimental confirmation. Higgs boson discovery. The existence of the Higgs field was confirmed by the discovery of the Higgs boson at the Large Hadron Collider, LHC, in 2012. The Higgs boson is the quantum excitation of the Higgs field and has a mass of approximately 125 GeV/C2. Precision measurements. The masses of the W and Z bosons, as well as the properties of the Higgs boson, have been measured with high precision, providing strong support for the electroweak theory. Summary. The electroweak theory explains how particles acquire mass through the Higgs mechanism. The interaction of particles with the Higgs field, described by Yukawa couplings, determines their masses. The theory successfully unifies the electromagnetic and weak forces and has been confirmed by experimental discoveries, including the Higgs boson. The electroweak theory, which unifies the electromagnetic and weak nuclear forces, has significant implications for our understanding of neutrino masses. Here's a detailed explanation of how this theory relates to neutrino masses. 1. Neutrinos in the Standard Model. Massless neutrinos. In the original formulation of the Standard Model, neutrinos were considered massless. This assumption was based on the lack of experimental evidence for neutrino mass and the simplicity it brought to the theory. Left-handed neutrinos. The Standard Model includes only left-handed neutrinos and right-handed antineutrinos, which participate in weak interactions mediated by the W and Z bosons. 1. 2. Neutrino oscillations. Discovery of oscillations. Experiments in the late 20th and early 21st centuries, such as those conducted by the Superchemical and SNO collaborations, provided compelling evidence for neutrino oscillations. Neutrino oscillations occur when neutrinos change flavors, for example, from electron neutrino to muon neutrino, as they travel to. Implication of mass. Neutrino oscillations imply that neutrinos have mass, as oscillations can only occur if there are differences in the mass states of neutrinos. This discovery necessitated a modification of the Standard Model to include neutrino masses. 2. 3. Mechanisms for neutrino masses. Dirac masses. One way to introduce neutrino masses is through Dirac masses, similar to how other fermions, like electrons, acquire mass via the Higgs mechanism. This requires the existence of right-handed neutrinos, which do not interact via the weak force and are thus sterile. 3. Majorana masses. Another possibility is that neutrinos are Majorana particles, meaning they are their own antiparticles. This allows for a different mass generation mechanism that does not require right-handed neutrinos. Majorana masses can arise from interactions that violate lepton number conservation. 3. 4. Seesaw mechanism. Type I seesaw. The most popular mechanism for generating small neutrino masses is the seesaw mechanism. In the type I seesaw model, heavy right-handed neutrinos are introduced. The interaction between these heavy neutrinos and the light left-handed neutrinos results in the light neutrinos acquiring very small masses. 3. Type 2 and 3 seesaw. Other variants, such as Type 2 and Type 3 seesaw mechanisms, involve different particles and interactions but similarly explain the smallness of neutrino masses through a balancing effect. 3. 5. Experimental evidence and constraints. Neutrino mass limits. Current experiments have placed upper limits on the masses of neutrinos. For example, the combined mass of the 3 neutrino flavors is constrained to be less than about 0.1 eV4. Neutrinoless double beta decay. The search for neutrinoless double beta decay is ongoing. Observation of this process would confirm that neutrinos are Majorana particles and provide direct evidence for lepton number violation. 4. Summary. The electroweak theory, as part of the standard model, initially did not account for neutrino masses. However, the discovery of neutrino oscillations necessitated modifications to include neutrino masses. Various mechanisms, such as the seesaw mechanism, have been proposed to explain the small masses of neutrinos. These developments have profound implications for our understanding of particle physics and the fundamental forces. That was all. Goodbye.